Hello, everyone. Can you hear me?
Yes.
Okay. I'm the session chair, Cuiyun from Harbin Institute of Technology. So welcome to this session. This session is about debugging, defect prediction, and fault localization. In this session, we'll have 4 research papers. And so let us invite the first presenter, Yuan from Binhang University. He will present his work, DependLoc, a dependency-based framework for bug localization. So let's welcome. Hello.
Okay.
Okay.
Okay, let's start. Hello, everyone. I'm Yuan from Binhang University, and today I will introduce our work, DependLoc, a dependency-based framework for bug localization. And the authors also include my colleague Binhang and my advisors, Professor Hailong and Xudong. I will talk about our work from 5 parts. So what is bug localization? It's also called fault localization, and it tries to locate where a bug occurs in files. Currently, there are 2 main techniques, spectrum-based and information retrieval-based. Comparing these 2 types of techniques, the first one is more accurate, but with high cost, because we need to run the program with different test cases, while the second one can achieve comparable performance, but with low cost, because it's mainly based on bug report. So IR-based methods are getting more and more attention. And in IR-based methods, each bug report is considered as a query, and it will return a ranked list of source files to be checked. But the problem for IR-based methods is that there is a lexical mismatch between bug report and source files. So to bridge this gap, some deep neural network techniques are introduced. For example, in MPCN model, the convolutional neural network is used to extract the structural information in a source file. And in the state-of-the-art work, DependLoc, they propose to use different word embeddings. And they consider the fixing history by saying, however, only for some application, the top 10 accuracy of existing approaches can achieve 80%. So the performance still needs improvement and more advanced techniques are expected. So where does our motivation come from? Let's see an example. This is a bug report from Tomcat, and it reports something wrong about credential and authentication. Below is a file list recommended by bug locator, which is mainly based on textual similarity. However, the real buggy file is ranked at 31st. When we check these files further, we find that 4 files in the top 10 ranking reference this buggy file. That is, they have a dependency relationship with it. Moreover, among the bugs that are not hit in the top 10 ranking by bug locator, about 1/3 of them fall into this case. So our observation is that buggy files may not be highly similar to a bug report, but have a dependency relationship with files that are quite similar to the bug report. So our goal is to capture the dependency feature, and we try to utilize this dependency feature to improve the accuracy of bug localization. Now let's see our approach. Our approach is called DependLoc, and it consists of 3 submodules. The first submodule is CN for TF-IDF. It tries to capture features from TF-IDF vectors as well as textual similarity. The second submodule is segment RefHI encoder. It will encode the document segments into vectors with dependency feature. And the third part is CN for RefHI. It will explore the relevancy on RefHI vectors. I'll introduce each submodule next. So let's see the first submodule. TF-IDF has been adopted in a lot of bug localization related work to measure the textual similarity. Suppose the vocabulary size is n, then each bug report file can be represented as this n-dimensional vector. However, if we only apply cosine on these vectors, we cannot capture other features. So CN for TF-IDF is designed to capture features other than textual similarity. And in this model, the TF-IDF vectors for bug report and source file are combined, and the convolutional kernel slides like this. Then after max pooling, the shape of the vector is showing this formula, and this vector will be merged later. So we are the first to propose input TF-IDF into DNN for bug localization. And in addition to texture similarity, this model can also capture other features, such as document length and similar bugs. Now this is the second submodule. As I mentioned, we try to utilize this dependency relationship for bug localization. So naturally, we can build a class dependency graph first. Here is the definition. If class A references class B, we call A depends on B. But note that simply using this dependency feature may bring many unrelated files. So we need to find a proper way to represent this dependency feature. And two conditions should be satisfied. It should effectively distinguish buggy from non-buggy files, and it should cover all source files in a project. So we propose to quantify this dependency feature by simulating the possible reference paths of classes, and we designed a customized end colony algorithm on this CDG. And here is the algorithm. So at first, each end is initialized, and it randomly chooses a node as a start. If the out degree of the current node is 0, it will choose another node as a start. If not, the end randomly takes the next step from the outgoing nodes of the current node. When the next node has been visited, we need to check. If the outgoing nodes of next node are all visited, which means this unvisited node set is empty, then the end stops. Otherwise, it will take node next as a next step. Here, the purpose of checking this unvisited node set is to prevent the end from getting stuck in the loop, because some classes are referenced each other. Then we can obtain the frequency of a class to be referenced by collecting all ends paths, and we call this reference heat. And here, this figure shows a distribution of accumulated reference heat on in-degree, out-degree pairs in Tomcat. And we can see that the source files with in-degree between 1 and 3 and out-degree between 0 and 1 are referenced most. And this figure also shows that source files with high in-degree or out-degree doesn't necessarily mean that they will be referenced frequently. So reference heat can reflect the importance of class in the dependency topology, but the value is discrete and it varies greatly. So after taking the natural logarithm of the reference heat value, we can divide them equally into NHI intervals called reference heat interval. And this figure shows the reference heat intervals in Tomcat, and 51 ref HIs are shown in these light blue dashed lines. And this figure indicates that we are not able to distinguish buggy from non-buggy files simply based on the reference heat values. Then we can create a NHI dimensional vector for each token. The idea for creating such token is that each token can inherit the reference heat feature from the source file where it appears. And with formulas, the ith token, the ref HI vector for the ith token can be represented as this Ti. Further, we can create ref HI vectors for bug report and source files, showing formula 6 and 7. Our goal is that given a bug report, we can match it with a buggy file through ref HI. However, the static vectors calculated by formula 6 and 7 are not sufficient to predict the target ref HI. So we designed a segment ref HI encoder. And at first, documents are split into same-sized segments. Then in this encoder, the segment tokens are embedded and input into CNN1. The detailed structure of CN1 is shown in this figure. At the same time, we create segment ref-HI vectors similarly to formula 6 and 7, then input these two vectors to CN2. And the output of CN2 is also an NHI dimensional vector, showing the probabilities of NHI intervals that the current segment belongs to. Then, with the segment vectors produced by the encoder, we can create new ref-HI vectors for bug report and source file. Here, QSEG refers to the segment vector produced by the encoder. And next, with these two new vectors, CN for ref-HI is deployed to learn the relevancy between them. And the output of CN for TF-IDF and CN for ref-HI are fused by FC layers, and the relevant score is generated, showing how likely the source code is relevant to the current report. Now let's see the experiment. So our benchmark datasets involves 6 Java projects, and these datasets are provided by this FSE paper. And this dataset has also been adopted in many previous bug localization work. In our experiment, we use Java-Lang library to parse a dependency relationship. And to guarantee the reliability of our result, we perform tenfold cross-validation. So in each project, the reports are divided by 811 for training, validating, and testing. And we also adopt 3 widely used metrics to evaluate the performance of DependLoc. They are top K accuracy, MAP, and MRR. And our experiment results are discussed through 3 research questions. So the first question is, how does DependLoc perform compared with existing approaches? So this figure shows the result of top K accuracy for 6 projects. And in general, the DependLoc performs best. The result of DependLoc are shown in these light blue lines. And the DependLoc outperforms the other methods, especially when K is larger than 2. To be more specific, we show the top 10 accuracy for each project. And on average, for top 10 accuracy, DependLoc is 4% higher than that of DeepLoc, especially on BERT. The top 10 accuracy is 8% higher than that of DeepLoc. And here is the MAP result. And it's also clear that DependLoc outperforms best. The second question is, how effective are the submodules in DependLoc? And this figure compares the top 10 accuracy for different submodules. And we can see that at first, CN for TF-IDF is compared with bug locator because the input of CN for TF-IDF is consistent with the most important input of bug locator, namely TF-IDF vector. However, we can see that CN for TF-IDF achieves a much better performance than bug locator. Especially on BERT, the accuracy is improved by 17%. And the performance of DependLoc relies on both CN for TF-IDF and CN for ref-HI. So by comparing the results of these 2 parts, we can see how much does CN for ref-HI contribute to DependLoc. And we can see that on average, the top 10 accuracy is improved by 5% compared with CN for TF-IDF. The third question is, why can reference hit help locate the buggy files? The first reason is that we find the proper way to quantify this dependency feature. And the key point is not the exact value, but the distribution of the reference hit. And this representation can cover all source files as well as new bug reports. At last, I will make a summary. So we're motivated by our observation. We are the first to propose a dependency-based framework. And to quantify this dependency feature, we proposed a customized end colony algorithm, and we define the concept of reference hit and ref HI. We are also the first to propose to use TF-IDF vectors as the input of DN for bug localization. And to guarantee the reliability of the outputs, we perform tenfold cross-validation. And the experiment results shows that DependLoc outperforms the existing approaches, and each submodule is proved to be effective. So for the future work, given that the relationship between classes may involve different types, so we plan to explore the dependency based on the edges in CDG. Okay, that's all. Thank you.
Okay, thank you, Yuan, for the presentation. So any questions to ask Yuan? Okay, if you have any question, you can raise your hand so the volunteer can unmute you. So I have one question. So the question is that why you choose CNN as the DN model, not other DN frameworks like LSTM, like that? Why you choose CNN for the DN part?
Okay, thanks for your question. So let me turn to the slide. So for example, in this submodule, CNN for TF-IDF, because the input vector is TF-IDF vectors, and we don't need to consider the order between each tokens. So we don't choose some deep neural networks such as Irman to capture the order.
Okay, so just like Battleverse model, right?
Yeah.
So have you tried to directly use word embeddings as input, like take the average of the word embeddings of the input?
For this model, because our input is TF-IDF vector, so we don't need to use embeddings. But in the second submodule, let me see. So in this submodule, we use word embeddings to embed our input tokens. Yeah, because in these segments, we need to consider their order.
Oh, I see. So thank you for your detailed answer. So any questions? So if not, let's thank Yuan and let's invite the next presenter, Bodin. Bodin will present their work, understanding the non-repairability factors of automated program repair techniques.
Okay, I'm here. Wait a moment. Let me share my screen.
Okay. Take your time.
Okay, can you hear me?
Yeah.
Okay.
So the PPT is already in present mode, right?
Okay, okay.
No. So how you? Yeah.
Let me start. Okay. Hello everyone, I'm Boling from National University of Defense Technology. Today my topic is understanding the non-repairability factors of automotive program repair techniques. This is our collaboration with research from Huazhong University of Science and Technology. As revealed by recent studies, existing literatures are mainly focused on the improvement of performance on eventually fixing benchmark bugs, while often ignore the failures of fixing attempts of bugs. For example, if a tool could fix a bug in an evaluation while it failed due to the configurable problem, like the Wang class path of Java program. Here is an example from Quiz XC 2020 study. When others used Zola 1.7 to localize the suspicious line, it gives an invalid suspicious value and triggers this exception. We regard it as the non-repairability factors of APR techniques. To fill this gap, we perform a large-scale empirical study to find out the factors that trigger the non-repairability exceptions. These 5 studies are selected as our study. Other APR studies only release parts of loss or none. Leo 2020 revisits the efficiency of test suite-based program repair by performing a large-scale experiment on 16 APR tools. Semifix is an APR technique that utilizes code change and operation from existing patches and similar codes to reduce search space. Wang reruns Semifix and Capgen on Mogito bugs. During 2019 consensus benchmark or fitting program through a comprehensive comparison of APR tools performance among 5 benchmarks. Martinez 2016 reruns J-Kali, J-Jinpok, and Noble on Defect 4J to evaluate their abilities for fixing real-world defects. Finally, we collect 11,818 loss in this study in total, which are generated by 11 APR tools on 395 defects for JBoss. Our goal is to analyze the non-repairability factors of APR tools. Here is our research questions. For research question 1, we search for the occurrence for all exceptions. For research question 2, we analyze the behind reasons for this unexpected exception. Finally, we investigate the impacts on the experimental results by recalculating the effectiveness of APR tools. This is the detailed experiment setting for RQ1. We need to find out all valid fixing attempt. Specifically, patch found is used to indicate the successful case for other laws, which based on different fixing strategies, we applied corresponding mapping subject to find out all exceptions. For example, in order to figure out whether the tool visits the whole search space or not, no Android value is used for constraint-based tool, like NOPO. Similarly, exhaustive navigate is used for search-based tool, which means the tool can find plausible patch due to the exhaustive of search space. We identified 3,035 exceptions from our dataset, which can be classified into 40 types based on exception messages, which account for 25.7% of all loss. This result indicates that a large proportion of fixing attempts suffered from the non-repairability factors during the execution, and it also demonstrates the importance of this paper to avoid the same problem in future studies. For review of different exceptions type, as indicated by the last column, the number of different types ranging from 3 to 1,128. Illegal state is the most common exception type, which has occurred for 1,128, account for 37.2 in all exceptions. On the distribution with respect to APR tools, we found that 11 APR tools suffer from the non-repairability factors in varying degrees. Specifically, Cardamom witnessed the most exceptions, 782 in total, which account for 25.7 in the entire set. The following are JMute repair and Jiechu pork, whose value are 529 and 478 respectively. In the perspective of distributions with respect to defect 4J projects, we found that closure projects include 1,158 instances, while only 65 cases in chart project. We note that different projects contain diverse number of bugs, hence from the view of how many exceptions happen for a single bug on average. The Mojito project achieved the highest value, since it only contains 38 bugs, but induced 608 exceptions when repairing the bugs. Here is the take-home message of RQ1. Firstly, the non-repairability factors affect a considerable number of phishing attempts, 25.7 of our study loss. Secondly, illegal state is the most common exception type, which accounts for 37.2% of the whole benchmark. The last one is that the distributions of these exceptions vary a lot with respect to different APR tools and the defect 4J projects. Here is our experiment setting of research question 2. We classify exceptions, different types of exceptions. We classify them into 5 categories. Note that our manual analysis shows that several exceptions are caused by diverse root case. We thus use sharp to denote different root case in a table. Generally speaking, inherent defects of APR tools is the most common type, account for nearly 60% of total exceptions. Due to the time limit, we only analyze for several wedged exceptions. Detail can be found in our paper and the project page. Here is a case of illegal argument exception. We found that some APR system execute defect 4J export-p cp.test to get the class path for compilation. However, this command will delete the build test file for some Mojito bugs. This is a bug from defect 4J and have been existed for many years. Here is a case of illegal argument exception. We found that some for localization tool only take the return statement as shown in slide as suspicious line under Xudong 0.1. However, some APR tools integrated in Austal system will mutate this statement but can generate any available mutation. We classify such bugs caused by library as inherent defects of APR tools. Here is a case of final found. We note that the latest Xudong version can be called directly as 0.1 version. Therefore, research chose to first execute this tool and record the results in file, and then read the full localization result from the corresponding file. If a researcher passed the wrong path to the program or there's no corresponding file under the path, the repair tool will expose such exceptions. We have confirmed this with the other of these tools. We last classified such bug caused by library as the improper operation of replication study. Here's a case of out of memory. As we know, executing API calls require high-performance servers since the search space is extremely large. If the computing power is not enough, some calls may run off the heap space or cannot allocate more memory and thus cause an error. We classify such bugs caused by computing power as low performance of machines. Here is the take-home message of research question 2. Firstly, the cases of non-repairability factors are diverse, which can be mainly classified into 5 categories. Secondly, inherent defects of APR tools is the dominating one, which accounts for nearly 60% of the total amount. We then recalculate the cost of different APR tools under different for localization strategies without considering the invalid phasing attempts. This graph lists the change of recall value when only considering valid phasing attempt. We found that the result of 30 of them have been affected by non-repairability factors. The only result remains unchanged is the dynamo tools under Zola 1.7 strategy. Such result shows that the non-repairability factors bring both impact on various APR tools under different for localization configurations. On the view of changes of recalls, we found that the change of recall value under most of the experiments is less than 2%. However, there are also 4 experiments value change more than 10%. Generally speaking, the changes on the Zola 1.7 are limited, where the maximum variance only reached nearly 4%. As a comparison, the changes under the perfect for localization are generally more obvious, since the number of valid attempts is sometimes less than 100, such as the valid attempts in JMUT repair is only 33, much less than the total number of bugs in Defect 4J, which is 395. As a result, its recall has increased by 30%. Through our Q3, we found that non-repairability factors are widespread among evaluation on diverse combination of APR tools and fault localization strategies. Furthermore, the changes of recalls vary for different experiments, range from 0 to 30%. This paper reports a large-scale empirical study on the exception of APR techniques. We show the frequency of occurrence, behind reasons, and its impact on the performance of APR techniques. We further discuss the several implications for eliminating biases which caused by such exceptions. All data is available on the node. You can scan this QR code to get it. That's all. Thank you.
Okay, thanks, Bodhi, for the presentation. There are some questions, as you can see in the message part. The first question is, what does no angelic value for constraint-based tools means in the page 4 of your slides?
Okay.
Yeah.
Let me see. Okay. In my opinion, for constraint-based tool, the tool will execute some tests or examples. As we know, the current APR tools is a test-based tools. It means it will execute some tests or examples. If a test pacing path is not detected, it means no angelic value. Only other way, for specific test passing path, if there exists have a specific way for each simple that can make this test pass, we call it angelic value. Okay, that's.
So does the answer match your question? Oh.
Okay, let me see the next question.
Yeah. So the next question is from Professor Abik. He asked you, can you kindly summarize the actionable points from your study? And another question is, how can we use your results to improve APR tools since you studied a diverse set of tools?
For example, I suggest that some others of APR tools they can focus on focus on some tiny question. For example, when we do this study, we try to give some. We try to fix some bugs in our machine. So maybe.
Yeah. So maybe I can clarify the question. Sorry, if
yes.
It is okay. Yeah. So you pointed to certain exceptions not being handled by the APR tools and also the role of the fault localization. I think that part is quite clear. But how can we use, I didn't see the actionable component here. This is the deficiency component. But how can we use this to improve? Of course, there would be one obvious way to improve, like corresponding to each of the exception types, we start adding templates to the APR tools. But probably that wouldn't be a very good APR tool if we just have one template for every possible exception, and we wouldn't be able to manage those things very well. And that would be more of a workaround rather than repair. So it wasn't very clear to me how we can take your study and have a clear improvement, like, okay, this is what we need to do for these classes of APR tools.
Yes.
Also, because you are studying many, if that is not something you have examined, that's okay as well. I was just wondering, yeah.
Yes, I believe that the most important thing is sometimes if for others, when they focus on, when they try to perform their study, they maybe try to filter out some invalid tests, or they have to they have to confirm the library is no buggy, or the library are up to date, or use use the machine which have enough power, such as that.
Okay. Thank you.
Thank you.
Okay. Thank you. Now, so let us move to the next speaker, Zhang Tianhang. He will present their work under software defect prediction and localization with attention-based models and ensemble learning. Yeah.
Hello, can everyone hear me?
Yeah.
Okay.
So please share your screen.
Wait a second. I'm sorry, there is some issue going on my computer. Let me fix that quickly.
Do you need us to present your video?
What?
Do you need us to present your recorded video previous?
No. Yes, I'm open. Yes. Wait a second. I need to restart my Zoom.
Oh, okay. So let us wait a minute. Maybe we can move to the last. Okay.
Okay. I'm good. Can you see my screen now?
Good.
Okay. I'm sorry for
It's
the
okay.
inconvenience. Okay. So hello everyone. My topic is software defect prediction and localization with attention-based models and ensemble learning. My presentation will be divided into 4 parts. The first part is the introduction to the topic and the relevance of the research. The second part is the current research status in this field. The third part is the introduction of the model proposed in my paper. And the fourth part is the summary and outlook. First, I would like to introduce what software defect prediction is. According to IEE standard definition, a software defect is an imperfection or deficiency in a work product where that work product does not meet its requirements or specifications and needs to be either repaired or replaced. Research shows that in the complex software system, defects are often inevitable and defect fixing requires a large number of human resources. Statistics show that more than half of the total cost of software development is spent on fixing defects. Therefore, if the defect in the software system can be identified in time at the software development phase, the cost of fixing defects can be greatly reduced. Next, let me briefly introduce the current status of research in the field of software defect prediction. Software defect prediction can be divided into 2 subcategories: within project defect prediction and cross-project defect prediction. My paper mainly focused on the within project defect prediction. Predictions can be made at file level, class level, and method level. Software defect prediction is a significant research topic in software engineering, and numerous studies has been carried out since Akiyama first tried to build defect prediction model using size-based metrics and regression modeling techniques in 1971. The various machine learning techniques are widely used for software defect prediction, such as logistic regression, support vector machines, naive Bayes random forest, and neural networks. The datasets that are most widely used by traditional machine learning algorithms are NASA MDP dataset and the PROMIS dataset. They both adopt manually designed metrics as a representation of the code snippets. However, a serious problem is that static code metrics of a defect and a non-defect code may be numerically identical, since defect characters are often deeply hidden in the complicated semantic of code context. It is arduous for code metrics to fully capture these characteristics. To cover the shortage of the static code metrics, research have used the deep learning techniques to extract features from ASTs and the control flow graphs of the code snippets and has got some achievement. But there is still another factor that constrains the model's prediction ability, the class imbalance problem. Previous research indicated that the distribution of software defects satisfies the 20-80 principle, which means 80% of the software defects are usually contained in approximately 20% of the system files. In these situations, the defective samples and the non-defective samples may be overlapped. Most previous research used oversampling or undersampling to balance the data distribution of a given dataset. Although the performance has improved, the final prediction results are still a little far from satisfactory. Besides, there are some other deficiencies in previous studies. Few published studies have attempted to make prediction at the code line level, which is urgently needed by developers to obtain more information. The second, the capability of traditional machine learning methods are facing increasing challenge as deep learning techniques become more and more sophisticated. Meanwhile, it has been reported that specific classifier tends to defect a unique subset of defects, which means the capability of a single classifier to find all types of defects needs to be improved. The third, the two widely used data set, NASA MDP and Promise, however, have problems such as insufficient data and a marked characters of class imbalance. It has also been demonstrated that the MDP dataset have the data quality problems. To address these deficiencies, we proposed a software defect prediction and localization model. The model utilized the attention mechanism and techniques to make prediction at the function levels, as well as locating the specific line of the code if the function is predicted as defective, which can provide a more detailed reference to the developers. We also proposed an approach for collecting and processing software defect data sets to address the potential problem in existing data sets. In the next sections, I will elaborate on the model construction process and the data pre-processing procedures. First, let me introduce our code representation schema. Since the abstract syntax tree of code can reflect the semantic and the structural info of the code context, we adopt it as a representation of the code snippets to make up for the deficiencies of the static code metrics. Moreover, as shown in Fig 1, the structure and the token of an abstract syntax tree do not depend on specific programming language. For example, the if-then statement often has different representation in different programming languages, but as in shown in Figure 2, the structure and the tokens are always the same. Leveraging these features, previous researcher proposed the code-to-vec model for the prediction of the method name and has achieved excellent results. Inspired by this model, we have improved on it to avoid the dependency on Kocanik method names and applied it to the software defect prediction problem as one of our ensemble learning models to participate in the final prediction. The construction process of the improved model is as follows. First, we use Java parser to extract the abstract syntax tree from Java code snippets. The extracted set of leaf node and path is then randomly initialized to a leaf node embedding matrix and a path embedding matrix to obtain their corresponding mathematical expressions. And the embedding vectors corresponding to an AST context are then stitched together to comprise the context vector. The context vector is then computed through a fully connected layer, the weight matrix of which is learned automatically during the training process. In order to efficiently extract the features of the code, the model randomly initializes an attention vector, which is learned during the training process and utilized to calculate a scalar weight to each of the combined context vectors by computing the normalized inner product between them, the result of which is the attention weight paid by the model to the corresponding path context, so as to identify the importance of different path contexts. Then the code vector is computed to represent the code snippets using a linear combination of the combined context vectors factored by their attention weights. The code vector is then fed into a 3-layer fully connected network and eventually outputs a binary classification probability for predicting the defect pronouns. For training the network, the binary cross-entropy loss is used to calculate the model loss. In this way, by modifying the training object, the improved model can capture potential patterns of defects from the abstract syntax tree and pay higher attention to the past context that may be related to the presence of defects, which can fully exploit the attention mechanism. Since the whole model training process does not involve function names, the dependency of the original model on the Kocanik method names is successfully avoided. Next, I will represent the second model participating in the final prediction. Since the difference between defect and non-defect code may be only a few changes of the node position in AST, only considering the past context is not enough. We need another feature extraction method which is more sensitive to the change of AST structure. Inspired by previous researchers' work, we finally choose a tree LSTM model and has also improved it for ingenious combination with the code-to-vec model. It is quite suitable to use a tree structure sequence to extract the feature of a code snippet from its AST, since the output of the root node will contain the feature information of all AST nodes. We achieved the node-level feature extractions. Besides, based on the improved version of the code-to-vec model, we can obtain an embedding vector for each AST node. The feature vector of the code snippets can then be obtained by performing a bottom-up transversal of the AST to extract the node information and the tree structured feature as shown in Figure 4. The tree transversal is done recursively by feeding each child node into a shared LSTM unit to obtain the hidden output state and the context vector, which will be part of the input of the parent node. In Figure 5 shows the internal structure of the LSTM unit. Notice that there is only one LSTM unit in our model. There are three main components in the LSTM unit: some forget gates, the input gates, and the output gates. Note that each child node corresponds to one forget gate, but the learnable parameters are shared. The functions of these gates are similar to those in the traditional LSTM networks and will not be repeated here. The output of the root node is the code vector we want. After obtaining the code vector, it is also fed into a three-layer fully connected network to obtain the predicted probability distribution, and the model is trained to minimize the cross-entropy loss until convergence. Meanwhile, we also calculate the attention value for each AST node. Since each AST node corresponds to a code block, after obtaining the attention value for each AST node, it is possible to calculate the attention value for each code line. Then we can sort the lines by attention value in descending order. The code line with the highest attention value will become suspicious targets that may cause defects. In our research, the most 5 suspicious lines are located to provide developers with more information if the method is predicted as defective. Until now, I have introduced the two classifiers, the improved code-to-vec classifier and the improved tree LSTM classifier. Since the final prediction made by the sublearner will consider all base classifier prediction results, more base classifiers are needed to achieve a better prediction performance. In our research, we choose random forest classifier as a third base classifier to precipitate in the final prediction, because it is also an ensemble learning algorithm with exceptional performance. The model construction process is similar to that of the traditional random forest algorithm. Just take the obtained code vector as training data and train the model until the decision trees cannot be split any further. The next step is to use the three models mentioned above as a base classifier and construct a sublearner model by stacking methods to obtain the final prediction result, as shown in As shown in Figure 5, the original training set is eventually partitioned into 10 disjoint parts to perform 10-fold cross-validation on each base model. Each time, 9 folds are selected as training set, and the remaining 1 fold is used as a validation set to assess the performance of each base model. The predicted value are collected as one part of the level 1 training data. With early stopping technology, the best performing model of the validation set is then used to be evaluated on the test set to obtain the prediction probabilities, which are collected as one part of the level 1 test data. After every fold has been picked as the validation set, we can obtain the prediction probabilities on each of the 10 folds and the 10 prediction results on the test set. This is all the data provided by the base classifier to the sublearner for training and testing. Then we need to train the sublearner to learn the optimal combination of these 3 base classifiers in order to prevent overfitting. The meta learner is generally a simple model. In this paper, as shown in Figure 7, a shallow neural network is utilized to fit level 1 training data, where the number of neurons in the hidden layer is 10. That is all the construction process of our ensemble learning model. The experiment results that shows that our ensemble model achieves better prediction performance than the constitute learning models after stacking. Now we have finished with the model. Let's move on to the data acquisition and pre-processing part. Most of the datasets used in previous studies cannot provide the specific code lines where defect exists, making it impossible to evaluate our defect localization method. Therefore, in our experiment, a method for collecting defect dataset is proposed. We use Python to crawl the code submissions from code forges as data source. It allows us to get the exact location of defects by analyzing the stack information in the code submissions we collected. For our experimental scenario, we select the submission with verdict runtime error as the source of defect samples because those programs crash during the execution often exist potential defects that cannot be detected by static code analysis and require a large number of test cases to identify. This situation is similar to the real world in software development. Besides, we choose the submissions with verdict accepted as the source of non-defect samples because they have passed various test cases and no exception was raised, which meets our requirements for non-defect samples. After obtaining the code file, we need to generate master level code files and clean the data. After cleaning, we got 120,000 non-defect samples with 2,400 defect samples, from which we can see that the ratio of non-defect to defect samples increases to 51:1. Given this, we employed a SOM clustering-based undersampling approach for our data. After clustering, we obtain the set of centroid for non-defect sampled and the defect samples. Then a score was calculated for each non-defect samples based on the cosine distance between the non-defect samples based on the cosine distance descending order. We remove the non-defect sample ranked in the bottom 30%, since the removal can make the boundary between classes more clearly. Then the remaining samples were randomly undersampled to generate a balanced training set. In summary, we propose a software defect prediction and localization method based on ensemble learning and attention mechanism. If a method is predicted to be defective, based on the attention mechanism, we can locate 5 code lines that are most likely to cause defects, which allows us to provide more detailed information to developers. To address the data quality issues that exist in the dataset widely used in previous studies, we propose an approach to collect the defect data by crawling the submission on code forces and then use the SOM clustering-based undersampling method to generate a balanced training set. The experimental results demonstrate the effectiveness of our model. It shows a remarkable improvement in both F1 scores and AUC compared with the other 4 machine learning algorithms. In terms of our defect localization method, the probability of successfully hitting the actual code line on the first attempt is 15%. The probability of successfully hitting the actual code line in 5 attempts is 51%. There are 4 main directions for our future research. The first is increase the number of base classifiers to make prediction more accurate. The third is explore innovative solutions for defect prediction at code line level. The third is defect prediction for other languages such as C++, Python, and so on. Thank you all for learning, for listening. My presentation is finished.
So any questions to ask Tianhang? Okay, I have a small question. So I want to make sure that the input of the tree STM is the whole AST. It's just one tree instead of a sequence of trees.
I'm sorry, I am not actually the author. I am a student from his lab. The author is now taking an examination. So I will tell him if you have really concerns, I will tell him your questions, and he will then email you about the answers. I'm sorry for that.
Okay, it's okay. Thank you. And if you have any question, you can also send an email to the author. Thank you. So let's move to the last presenter, Irman, Faqrizal, and Gwen Salaun. I'm not sure whether my pronunciation.
No problem, no problem.
Okay.
I'm here.
Okay. Yeah. Okay, it's your turn.
Okay, no problem. I'm going to share my screen. Okay, I'll start now.
Yeah.
Okay, very good. Okay, so hello everyone. I'm Gwen Salaun, and I'm going to present this work entitled Clusters of Faulty States for Debugging of Behavioral Models. This is a joint work with Irman, Faqrizal. So model checking aims at verifying that a model satisfies a temporal property. We use labeled resonance systems, LTS, as behavioral models in this approach. LTSs can be obtained from a higher specification language, as shown on this slide. If the property is not verified, the model checker returns counterexample, which is a sequence of actions leading to a state where the property is not satisfied. One of the main issues with model checking techniques is that understanding the counterexample is a difficult task. First of all, the counterexample can be quite long and can consist of many actions, hundreds or thousands of actions. Second, the debugging task is mostly achieved manually, and there is no widespread tool for supporting and simplifying the debugging phase. Third, the counterexample does not precisely indicate the source of the bug. The user has to go through all the steps of the counterexample to hopefully find an explanation to the bug. And last but not least, the counterexample does not emphasize any relevant action in the counterexample that might be the source of the bug. It just gives an execution trace that causes the bug. So this work relies on Gianluca Barsbourg's PhD thesis that I'm going to summarize in a few slides. So the main goal of Gianluca's thesis was to simplify the compression of counterexamples. To do so, his idea was to improve the counterexample representation to identify relevant actions in this counterexample that are more relevant than other ones from a debugging perspective. The first key idea to do that was to type or color all transitions in the LTS model using 3 colors. Green or correct transitions correspond to a part of the model where the property is satisfied. Red or incorrect transitions correspond to a part of the model where the property is not satisfied. Black or neutral transitions correspond to a part of the model where a correct or an incorrect part of the model can be reached. The second key idea is to use these colored transitions to identify specific states where there are several outgoing transitions with different colors. These states are called neighborhood or faulty states. There are 4 kinds of or types of faulty states, as shown at the bottom of this line, and they are usually visually represented using shades of yellow-orange. So Gianluca proposed different algorithms for coloring LTSs and computing faulty states depending on the kind of property, so safety or liveness. Once faulty states are computed, there are 2 ways to exploit them. The first option proposes a visualization of the entire faulty part of the LTS with faulty states. So appearing, as we can see on the right of this slide, with shadows of yellow, let's say, depending on their types. A second option is to build abstraction of counterexamples by emphasizing parts of the counterexample where there are faulty states, as shown at the bottom of that slide. All these ideas have been implemented in a tool called Clear. This tool consists of 3 modules, 1 module for computing faulty states, 1 module for visualization, and 1 module for building abstracted counterexamples. Let us now focus on visualization. What is interesting is that in some cases we can see that faulty states form some kinds of groups, as it is the case in the example at the top right. But in other cases, visualization is not so helpful. This is the case when the faulty part contains too many states and transitions, as we can see at the bottom left of these slides. This is also the case for smaller examples with not so many states and faulty states, but no clear relationship between these faulty states, as it is the case at the bottom right of this slide. So in this work, we define a notion of clusters of faulty states that aim at simplifying the debugging task, as we'll show later on with a case study. A cluster is a group of faulty states and is defined as follows. Each state in a cluster is of the same type or color. All faulty states in a cluster have at least 1 common ongoing label, meaning they correspond to the same portion of specification. And finally, there is 1 faulty state in the cluster from which all the other ones are reachable. We also keep in the cluster all labels appearing on all outgoing transitions for all faulty states in the cluster. This last information is useful to precisely identify the portion of the specification corresponding to this cluster. The main algorithm to compute all clusters works using a depth search traversal of the faulty part of the LTS. When it encounters a faulty state, it goes backwards to be sure not to miss a state in this cluster that would not be reachable from that state. If it does not find such a state, it traverses forward the reachable part of the faulty LTS to identify all faulty states in this cluster. Okay, I will now present a concrete example to illustrate our approach. This case study focuses on a smart home application. This application consists of 5 devices: a motion sensor, a light, a connected window, a temperature sensor, and a global switch to turn off all electric devices in the house. These devices interact as defined in a set of IFTTT rules, if this then that rules. For instance, if someone enters the house, turn on the light. If someone leaves the house, turn off the light. If temperature goes above the threshold, open the window. If temperature goes down the threshold, close the window. If it's late at night, for instance, switch off the power supply. If it's early in the morning, switch on the power supply, and so on. We can have more rules. So this application was specified in LNT, a modern algebraic language. Each device is modeled using one process for describing its behavior and one process for describing its put message buffer. Another process encodes all IFTTT rules, as we can see on the right. A main process specifies how devices evolve with event triggering and rules execution. Here is the main process. We can then verify several properties of interest. For instance, we can check that the power supply should not be switched off if the light is still on, because it can be dangerous for people still awake at that time. This is formalized, this is a temporal property, and this is formalized using the MCL language, as shown at the bottom of this slide. So the property is not satisfied by the LTS model generated from the LNT specification. When looking at the faulty part of the LTS, one can see that there are possibly 2 clusters. One consisting of a bunch of yellow states, and another one consisting of a bunch of orange states. However, this visualization does not give any information about the source of the bug. The cluster computation confirms that there are 2 clusters. By looking more precisely at the details of these 2 clusters, we can see that all labels identify the rules process, meaning that the bug should be located in this portion of the specification. Another interesting point is the action late, which appears in green in the first cluster and in red in the second cluster. When going back to the LTS, we can see that the light on action systematically appears between the 2 clusters, and that this action is not followed by any light off action. When looking at the rules process, we can see that the first rule, where the light is switched on, is unrelated to the following one, where the light is switched off. The first solution to avoid this problem is to switch off light when late before applying the global switch off. Okay. Another solution is to prevent the global switch off if there is still a light on. There is another piece of specification where it is possible to switch on the light at any time. This does not make any sense and actually corresponds to a buggy encoding of a rule. the simplest solution in that case to remove this piece of code. Once these two bugs are corrected, the model checker returns true for the given property. This is not time to conclude. Faulty states are specific decision points that make the specification execute a correct or an incorrect behavior. When a property is violated using model checking techniques, the model may exhibit many faulty states, making their analysis difficult. In this work, we propose to group similar faulty states into clusters. Each cluster aggregates information about the bugs, which is helpful for identifying them. The computation of clusters is fully automated by an extension of the Clear tool. It is worth noting that faulty states are not always helpful. This is the case, for instance, when the whole LTS is false, there is no faulty state in that case. It's interesting to note that there is no correspondence between the number of clusters and the number of bugs. In the example on the right of this slide, for instance, there are two clear clusters, but a single bug. As far as feature work is concerned, we'd like to see whether the notion of clusters could be improved or refined, because we observed that in some specific cases, a too large number of clusters is computed. This is the case when faulty states do not have the same type, or when they have the same type but no common labels. We also plan to improve the cluster computation algorithms to reduce their complexity. Thank you very much for your attention, and feel free to ask any question.
Okay, thank you for the presentation. So any questions to ask Gwen? Yeah, any questions? If not, I have one small question. So in the first few slides, you classify the drivers to correct, incorrect, and neutral. So what about the neutral ones? How to define the neutral ones? Yeah.
Usually you find neutral when there are no correct, neither incorrect. Basically, you start finding the correct and incorrect part that you can easily find using the property. Basically, you transform the property into Bucky automaton, and then you easily find the correct and incorrect ones, and all the other ones are neutral. Okay.
Another question is, how do you define the cluster in your paper? In the end, you talk about that you can have several types of classification, several types of definitions of the cluster. So what's the definition of cluster in your paper?
So now you have several types of clusters. Actually, they're mostly related to the type of faulty states, okay? Basically, you have just one kind of faulty states by cluster. Or if I put it differently, all faulty states in a cluster have the same type or color, okay? So, and this is one thing we would like maybe to improve, because we noticed that in some cases, you have several faulty states located in the same portion of code. They are reachable, and they have also the same outgoing labels, but they have different types, and this can happen. And in the current version of this work, we classify these different faulty states in different clusters. So it's why I would like maybe to improve, to think more about it, and try to refine to, in this case, which happens from time to time, to have these different faulty states, different because they have not the same time, in the same cluster. But we don't know how to do or to compute it already. We have to think about it, actually. It's tricky.
Okay. Thank you for your sharing.
Thank you.
Okay, this is the end of our session. So let's have a break. Yeah. The next session will start at around 15:40. Yeah, in the afternoon.